You ever find yourself driving across one of those long, super elegant concrete bridges and just think, how? How on earth does something that looks so slender, made out of what's basically fancy rock, stretch across this massive gap without just cracking right in half? It almost feels like it shouldn't work.
Right, let's get into it. We all think of concrete as being unbelievably strong, and it is when you're squishing it. But the moment you try to pull it apart, put it under tension, it's shockingly brittle. It just snaps. So there it is. That's the big mystery. How are we building these gigantic structures that are constantly bending and pulling under their own weight, not to mention traffic, with a material that has this one critical, hidden flaw? Well, the answer is genuinely one of the most brilliant, kind of counterintuitive ideas in all of modern engineering. It's not about just adding more stuff to the concrete, it's about giving it a superpower before it even gets to the construction site. The secret is a permanent built-in squeeze. So, what makes this squeeze so revolutionary? To really get it, we first have to go back to the fundamental problem engineers were trying to solve, that hidden weakness baked right into concrete itself. Okay, so traditional reinforced concrete is pretty straightforward, right? You just pour concrete around some steel bars. When a load makes that beam bend, the concrete on the bottom cracks, and then the steel inside kicks in to handle the tension. The key word there is then. It has to crack first. But pre-stressed concrete, or PSC, completely flips that on its head. It uses these super high-strength steel tendons to squeeze the concrete to put it into compression before it ever has to support anything. So now the concrete is already fired up, actively fighting against any pulling forces from the get-go. Let's put some real numbers to this so you can see just how huge this problem is. Imagine a pretty standard 30-meter bridge girder that's almost 100 feet long. Just from its own weight and the traffic on top, the pulling force, that tensile stress at the bottom of the beam, works out to a massive 62.5 megapascals. To put that in perspective, that's like 600 times the pressure of the air around you, all trying to rip that one single beam apart.
And here's the kicker. How much of that pulling force can high-strength concrete actually take by itself? A measly 4.2 megapascals. That's not even close. The load is more than 10 times what the material can handle. The beam would be torn to pieces. And that's exactly why just throwing some regular steel bars inside wasn't going to cut it anymore. We needed a much, much smarter solution.
And that smarter solution, of course, is the secret squeeze. This is where we stop talking about the problem and start looking at the truly elegant engineering that solved it. This is all about making the concrete itself work smarter, not just making it bigger. So here's the official definition, and I want you to focus on one word, because it changes everything. That word is before. By introducing this internal squeeze before the bridge even sees a single car, we're basically giving it a defensive shield in advance. The concrete is now actively pushing back against the tension it knows is coming its way. And the payoff for this clever trick? Oh, it's huge. This is what lets us build those incredibly long, graceful bridges. It means we can use thinner, lighter slabs, which saves a ton of material and weight. The structures don't sag as much over time, they basically eliminate cracking, and we're using every bit of material in the most efficient way possible. It's a total game changer. Now, it turns out there isn't just one way to do this. Engineers have come up with two main recipes, if you will, for applying this squeeze, and they picked the right one for the job. The two methods are called pre-tensioning and post-tensioning, and honestly, the names tell you everything you need to know. In pre-tensioning, you stretch the steel tendons before you pour the concrete. This is usually done in a factory setting for things like those big bridge beams. In post-tensioning, you pour the concrete first, leaving these little hollow tunnels inside of it, and then you come back and tension the steel after the concrete's already hard. This is super common for building floors right on the construction site.
So let's walk through pre-tensioning really quick. Picture a super long factory floor. First, they stretch these high-strength steel strands between two massive concrete blocks. Then, they pour the concrete right over those tension strands. After the concrete cures and grabs onto the steel, they just cut the strands loose. The steel wants to spring back to its original size, and when it does, it squeezes the concrete with all that stored energy. And just like that, you have a pre-stressed beam.
Post-tensioning is a little different because it happens out in the wild. Here, you start by laying out hollow tubes where the steel needs to go. Then you pour your concrete slab. Once it's all cured and hardened, you thread the steel tendons through the tubes, grab them with these incredibly powerful hydraulic jacks, and just pull. Once they're stretched to the perfect tension, you lock them in place with special anchors, and that squeezing force is transferred right into the hardened concrete.
So we've got the theory down. But what does this actually look like when you're building something truly enormous? Let's go back to our bridge girder and look at the insane forces we're talking about here.
Okay, first, the scale. We need this one beam to span 30 meters. That's nearly the length of a full-grown blue whale. That is a crazy distance for a single piece of concrete to stretch without any support in the middle.
Now, to counteract the incredible bending force that a span like that creates, the engineers calculate they need to squeeze that beam with, get this, 13,333 kilonewtons of force. That is the same as stacking almost 300 full-grown elephants on the very end of the beam. It's a mind-boggling amount of compression.
So how in the world do you create that kind of force? Well, you pack that beam with power. That one single beam contains 68 individual strands of high-strength steel, each one stretched tighter than a guitar string from hell, all of them working together to create that secret squeeze. That is the hidden power holding up our world.
But look, harnessing this much power is not easy, and it is definitely not without risk. This isn't just about brute force, it's a high-stakes game of precision engineering where the margin for error is razor-thin.
For every single thing that can go wrong, there is a meticulous plan to stop it. If a tendon is just a little bit out of place, it could weaken the whole beam, so they do constant profile checks. If the jacks pull too hard and overstress the steel, they could literally crush the concrete, so every single jack has to be perfectly calibrated. It is a field that is absolutely obsessed with control and precision.
And you know, this quote from the source material just hits the nail on the head. It says, "Pre-stressing is way less forgiving than normal concrete. A tiny mistake out on the job site can have a massive impact on how strong the final structure actually is. The stakes could not be higher."
And because those stakes are so high, the whole process is built around these things called critical hold points. These are moments where all work just stops, dead, until an inspection is passed. Is the jack calibrated? Hold. Is the tension in that strand exactly what it's supposed to be? Hold. Is the concrete actually strong enough to handle the squeeze? Hold. Nothing, and I mean nothing, moves forward until it is proven to be absolutely perfect.
So the big idea here is this. That simple, almost backward-sounding idea of squeezing concrete before you use it has literally shaped the modern world. It let us build longer, lighter, and stronger than ever before. It really makes you wonder, doesn't it? What's the next big breakthrough going to be? What's the next secret squeeze that's going to build our future?